I'm David Chappell. Welcome to this talk on Windows HPC Server. Here's what we're going to do. We're going to start with the basics of cluster computing. What do we mean by cluster computing? How does Windows HPC Server fit into this world? After that, I'm going to talk about different kinds of apps. The four categories, at least as I see them, that you can think about the apps that run on HPC Server as fitting into. And finally, take a little bit deeper look at the technology, a little bit deeper, of Windows HPC Server. Here's what we're going to do. Let me say several things before we start. First of all, this is a 200-level session, right? It's the very last slot in Tech Ed. I don't know why it's now, but it's a very beginning session. I'm assuming no background at all in this space. Okay? The notion here is that I certainly believe there are in the world plenty of people today who use Windows who could very well benefit from Windows HPC Server, except they have no idea what it does. So that's one of the big goals of this session, is to help introduce this technology, people who know Windows but have no grasp of the HPC space. Second, look around the room. Are there, 12 people here? Maybe 15, generously? You're thinking to yourself, whoa, now here's a topic nobody cares about, right? 15 people. Well, let's think about that. First of all, it is the very last session on the very last day of Tech Ed. The party is only an hour or so away, right? That's bad to start with. But suppose this talk were in fact given back on Tuesday of Tech Ed, when it should have been. Would the room been full? I don't know. Because the reality is that Windows HPC Server is often viewed as a pretty darn specialized topic, of interest really to this pretty small group of people. And yet I would assert, in fact, it is the overriding thesis of this session, that we are very likely at the beginning of a renaissance in cluster computing, where this technology, which has been specialized, of interest to relatively small groups, is very likely to become much more broadly applied. And the reasons for that, we'll see, are both because the kinds of systems we can use to construct these clusters have expanded substantially, and, even more important, the kinds of apps we can run on these clusters have also expanded. So, with that as preamble, let's go. The basics of this technology. I despise technical presentations that dive right into solutions without describing the problem. What are we trying to do here? What is the problem we're trying to solve? The problem we're trying to solve is the following. It is that some apps are just too slow. That's the core problem. In some cases, slow apps are just slow apps. We're stuck with them. If an app has to process its data sequentially, it must do this, then that, well, life is full of pain, okay? But there are many scenarios where it's entirely possible, as my slide says, to take the app's logic and break it up into chunks and run those chunks in parallel at the same time, simultaneously, on lots of different computers. Great. That is the problem we're trying to solve. That is what this is all about. Making apps go faster by breaking them into pieces, into chunks, running those chunks in parallel on different computers. To do that, we create a compute cluster. The word cluster is grossly overloaded. There are all kinds of clusters. There are SQL Server clusters. There are web clusters. There are Hyper-V clusters. Forget all that for the next hour or so. We're talking about compute clusters. A different idea. Arguably, in fact, the first use of the word cluster, but I don't know. So you might think, if I've got an app that I want to spread across a bunch of machines, it's a simple problem. I can do it myself. And of course, you could do it yourself. But it's harder than you think. To take an app, break it up effectively, run it, use those machines well, it is harder than you think. So in practice, what people typically do with clusters, compute clusters, is they use software that's intelligent enough to help them with things like creating and managing the cluster, like scheduling the applications that run on the cluster, and more. That's the idea. So, when you think about clusters today, I think it's important to realize that what that word means has actually changed somewhat over the last, couple of years. Again, that's one of the core underpinnings of my thesis about the likely renaissance of cluster computing, that we're seeing new kinds of nodes be usable in clusters, and thus barriers to entry are going down. So, what is a cluster? It's a bunch of machines that can act in a unified way to run parallel applications. Now, the word parallel is, of course, also overloaded. By parallel here, I do not mean necessarily apps running on multiple cores of a single CPU, which is entirely possible. It may well be that an app running on a cluster has one or more of its chunks running on a multi-core machine and running those things in parallel. Sure, that's fine. But by parallel here, what I really mean is apps where the chunks run on different machines, even if those machines have only one core each. They don't have to, but they could. That's what parallel means in this context. So a cluster is a bunch of machines that work in a unified way to do this. Modern clusters, I would argue, are built from three kinds of compute nodes. Number one, servers, obviously. Big racks full of servers have been the conventional way people have built clusters since the dawn of cluster time. Great. And now, because the cloud is out there, we've got to say servers running on premises. For those of you who are not zen with cloud terminology, on premises just means not in the cloud. So it means in your data center or in your laptop or whatever, okay? So one of the core kinds of nodes one can have in a cluster, compute cluster, is servers, in racks, in some data center, in your organization. Great. In fact, arguably, that's the majority of nodes in compute clusters today. Option number two, however, desktop workstations. We have all these machines sitting on people's desktops, which increasingly have vast amounts of CPU power and plenty of memory, and they're unused big chunks at a time, like all night. Why not make it possible to add those to clusters at least some of the time? Now, obviously, no one is suggesting that users, busy doing Excel or Word or something else get kicked off from my cluster job. But if they're not using their machine, then why not use it? Adding desktop nodes to your cluster gives you CPU power for free, effectively. Option number three, the newest kind of node we see in compute clusters, servers running in a public cloud. It is this addition that I'm going to argue really makes clusters a lot more approachable. And here's why. Conventionally, to build a cluster, I had to buy a bunch of servers, install them, maintain them, run power to them. Big investment. I want to do things like make sure I use them all the time. I'd only do this if I had vast amounts of work for the cluster. As a result, what kinds of organizations could build applications that use clusters? Answer, big ones. Big ones could do it. With the cloud, however, it is possible to create clusters essentially on demand, where you bring up nodes, you pay by the hour for what you need, shut them down when you're done. The advent of the public cloud, I believe, is transforming how we can think about how we can use clusters. It democratizes access to this kind of parallel computing power. So, I can have a cluster that contains on-premises servers, desktop workstations, nodes in the cloud, servers in the public cloud. When I run an application on this cluster, the application's logic gets broken into pieces and run across those different systems. Now, of course, any given cluster might contain only on-prem servers or only public cloud servers or combinations of these things. But throughout my talk here, I'm going to show all these options all the time to emphasize this key point, that in the modern world, you want to think of clusters in this diverse, somewhat heterogeneous way. The notion of clusters as just a bunch of expensive servers in your organization is over. And again, that's a big part of why, I would argue, larger sets of people ought to care about this thing called Windows HPC Server. Because what it is a technology that does just what I've been saying. It's a version of Windows Server that has added to it software for creating and using and managing a compute cluster. Now, this talk is about the forthcoming, most recent version of this technology, which has the memorable name Windows HPC Server 2008 R2 SP2. And maybe you're wondering why I list the service pack number. The reason is that unlike many Microsoft technologies, these guys are perfectly happy to ship whole new feature sets in service packs. So it turns out there's a really important feature set I want to talk about that's in SP2. So that's why I call out that specific release, what we're talking about. In Windows HPC, your cluster can include, in fact, it must include, something called a head node, which always runs on premises. Today, at least, head nodes always run on premises, not in the cloud. And then it has some number of compute nodes, which can run on premises or in the public cloud, which in this case means on Windows Azure. It looks like this. My cluster can have on-premises servers running Windows HPC Server. It can have on-premises desktops running Windows 7. It can have cloud nodes in Windows Azure. Any of those. Then, there's a head node, which is on-premises. The head node runs Windows HPC Server. And on that instance of HPC Server, we have software to help us create and manage our cluster. We have software to help us schedule jobs on that cluster. Brief digression. The world of cluster computing has its roots, in fact, more than its roots, big parts of its trunk today, in this somewhat specialized world of scientific technical computing. In that world, there's a whole set of jargon which might not be familiar to you. For example, people almost never say application or app. They almost always say job. And I will use those terms interchangeably here in this talk. Also, in a lot of that world, people never say program. I'm going to write a program. I've got a program for this. They call them codes. Where's my code? It's remarkable. Long ago, I worked for a company called Cray Research. Cray Research was founded by Seymour Cray, one of the creators, the originators of this whole idea of massively powerful computing. And in that world, we use all this funny jargon. When you come to it now from the vanilla Windows world, it can feel kind of strange, but don't be confused. All right, so the job scheduling piece of HPC Server does what it sounds like. A user, you for example, might be sitting at a workstation. You might submit a job to the job scheduler. We'll discuss a bit more how this works later on. But the job scheduler then causes the job to run. It gets deployed across multiple nodes in the cluster, and it executes. Wonderful. There you have it. The basics of Windows HPC Server in 10 easy minutes. With me so far? Okay. Great. That's what it is. The point is to let us run applications faster. Next question, what kinds of applications? What kinds of things can I do with this technology? Well, it turns out that today, or at least where today means HPC Server 2008 R2 SP2, it is useful, I think, to categorize the kinds of apps this guy could run into 4 groups. 4 kinds of apps. You know, there are various ways to do this. This is the one I find the most useful. I would not say it's the only way, certainly. Number 1, MPI applications. Number 2, embarrassingly parallel applications. And I'm not kidding here. This is what they really call them in this world. I'll tell you why in a few minutes. Number 3, Excel applications. Number 4, the newest, big data applications. Let me walk through each of these categories and talk about what they're like, what they're commonly used for. Once we've done this, I'll go back to HPC Server and look a little bit more at the technology itself, what it does, what's going on. Let's start with MPI applications. This is where this all began. Probably fair to say today that most clusters out there were created originally for MPI apps. Probably fair to say. Okay, what are they? MPI apps are applications in which the different chunks of logic in your job, the components in your job that are running on different computers, talk to each other while they run. They do some work, they talk to their peer. This guy does some work, maybe talks to some other peer. They talk while they execute. And they communicate using an API called the Message Passing Interface, MPI, hence MPI jobs. Now, just to be clear, MPI is an API, not a protocol. And so how they actually communicate given cluster technology is defined by that cluster technology. This is not about interoperability across clusters. It's about portability. The goal is to make it so that software and software developers can move effectively across different cluster technologies with the same APIs. So MPI is a standard in this world, been around for a long time. It's not the only option. It's by far the most commonly used option for building parallel applications on clusters where the components talk to each other while they are executing. Okay? Now, you recall the whole point of clusters is to make jobs run faster. If you have to communicate with each other during execution and you want that to be fast, are you going to use, I don't know, 100 gig Ethernet? Ideally, you are. You can use 100 meg Ethernet? I don't think so. What people commonly do here is create clusters that have high-speed connections, like InfiniBand, between them. So clusters designed for MPI jobs will care a lot, typically, about that kind of situation. They'll often put high-speed networks between their computers. Now, in Windows HPC Server, I can do these, going forward, with clusters using any kind of systems. Desktops, servers, Windows Azure nodes. But be aware, Windows Azure doesn't have, at the moment, this kind of high-speed network link. So some kinds of jobs are not going to work perhaps as well in that kind of cluster environment. There are variations here is the point, where some kinds of apps in some scenarios will work better with clusters built from some kinds of hardware. What do folks do with these? Well, the most common scenario for MPI jobs is some kind of simulation. Car crashes, nuclear reactions, building materials, all kinds of things. The goal usually is to help an organization figure out how something will behave in the real world without actually building it. So for example, I'm a car company. I want to know what happens to my car when it crashes into a wall at 40 miles an hour. Option number 1 is to just crash a lot of cars into a wall and go measure and see what happens. Right? I can do this. It's expensive. It's painful. It's time-consuming. If I can construct a mathematical model that does that same thing reliably, whoa, that's great. That's great, and you can do that. There are in the world packaged applications you can buy to do that. Those packages are commonly used by car companies today. They'll let them run simulations and learn about stuff without ever having to do the thing itself. That's a primary goal, a primary use of these kinds of apps. Not the only one, but a primary use. And so for a long time, cluster computing was all about this. That's what it meant for a long time. And that's very important. But if that were the only thing clusters were about, my guess is that many of you would not be here today. And I got to tell you, I would not be here today. Because that's interesting. It's useful, it's important, it's specialized. It's also not a really rapidly growing market. However, with the advent of clusters that can contain Windows Azure nodes, think about that. Lots of firms could benefit from this software, but they can't afford a cluster. They're small to mid-sized companies. With Azure nodes, you need not buy a cluster anymore. You can rent the nodes as you need them. Now, as I said, there are some limitations. You'll have slower interconnects on Azure. And it's possible that some of the apps you want to run aren't available on Azure yet. But going forward, one can expect these challenges to be met. And so what we're seeing here is the beginning, again, of the democratization of access to this functionality, letting smaller and mid-sized companies do this kind of thing. That's a good thing. You might think about these like this. A client submits an MPI job to the cluster, and the cluster's logic starts running. Those orange boxes are machines. Those pinkish purple ovals are the logic components of the job. The key thing about MPI jobs, the components talk to each other. They interact, they communicate, okay, via MPI. Contrast that with category number 2, embarrassingly parallel applications. Embarrassingly parallel applications are similar in many ways to MPI jobs in that they run logic on different computers, obviously. All apps on clusters do that. The big distinction here between MPI jobs and embarrassingly parallel jobs is embarrassingly parallel job components do not talk to each other while the job runs. This, in fact, is why they're called embarrassingly parallel. Because here's the deal. Writing an MPI app is potentially challenging. Because your MPI app has to have components that talk to each other at the right time. Lots can go wrong. Right? It's not so simple to write these things. These kinds of apps, each component just runs all by itself. That's pretty simple to write, at least compared to MPI. In fact, some developers felt they were so simple to make parallel that it was embarrassing. Hence the name embarrassingly parallel jobs. When I first began working in this space, I could not believe they actually use this term. But they do. It's the accepted industry term for this category of application. Embarrassingly parallel. So, and that's why. In Windows HPC Server, there are 2 big categories of embarrassingly parallel jobs. Number 1, parametric sweep. That sounds so cool, doesn't it? Who wouldn't want a parametric sweep job? But the concept is incredibly simple. All it means is taking an app, an XE, and running commonly the same XE on the machines in your cluster in parallel on different data. It just means running a bunch of apps, or the same app, many copies, on lots of machines. Great. But it's called parametric sweep, which sounds way cooler, I think. I like that. Option number 2, SOA jobs. SOA, as you might know, is an acronym for Service-Oriented Architecture. The notion here is that rather than running XEs, standalone apps, on the nodes in your cluster, you run services built using Windows Communication Foundation, WCF. What's cool about this? What's cool about that is I can interact with them. MPI jobs are most commonly batch. Submit them, they run, get the result. SOA jobs are most commonly, they don't have to be, but they can be interactive. Because I'm exposing services I can actually talk to while things are going on. What do people use these for? Well, there are a lot of examples, but the most common one today in the Windows HPC Server world, at least, is some kind of financial services scenario. For instance, suppose you want to estimate the likely price of a bond 10 years from today. Well, the bond's price will be a function of things such as interest rate changes over those 10 years. There are many possible changes, many possible paths between now and 10 years from today. If I can simulate the bond's price through a 10-year period with multiple interest rate changes, and do that through many possible futures, I can then get a reasonable idea by averaging those together of what the bond's price is likely to be in 10 years, and thus price it today. This is called a Monte Carlo simulation, Monte Carlo method. And it's a common way to use clusters and use SOA applications. Financial services people use this a lot. It's probably obvious, right? It's worth a lot of money. Pricing a bond correctly, getting even this much closer, is worth a lot of money. And so to invest the time and effort in doing clusters has value for them. And once again, traditionally, this required a cluster, servers in your data center, all that stuff. Now, here at the beginning of the renaissance of cluster computing, you can do this in the cloud. And MPI apps, remember, MPI apps tend to want fast network connections, which aren't in Azure today. These guys don't. A better fit for the cloud than MPI? Maybe. The point is, once again, we have democratized access. This is accessible, and we'll see. Windows HPC Server has built-in support for this today, doing this today. Now, just to be clear, financial services aren't the only way to use this. There are lots of others. I live in Berkeley, California, outside San Francisco. I live in the hills. And from my house, I can just about see Pixar, which is right down below me. Pixar generates these massive amounts of information on movies that make digital frames. Rendering the frames is done in parallel. It's a good example of what you might use an embarrassingly parallel technology to do. So, that was number 2. Number 3. Think about this. I told you that a primary user of embarrassingly parallel jobs is financial services. Well, it's common to give the application a user interface that a financial analyst finds comfortable. Well, what interface do most financial analysts find most comfortable today? The answer is Excel. Right? They live in Excel. So, gee, why not just use Excel directly? Now, here, I'm showing you the embarrassingly parallel situation, pictorially like you saw it before. It's like MPI jobs, except the logic does not communicate. I might interact with them, and the results come back. That could be anything. It could even be Excel. Even though I've called out Excel as its own category, the truth is that Excel jobs are basically a subset of SOA applications in particular, or embarrassingly parallel in general. So the notion here is this. The notion is that I have 3 ways to use Excel on a cluster with Windows HPC Server. Number 1, I can run Excel 2010 on each node in the cluster. I can then, for example, run the very same workbook on all those nodes, each one processing different data. And you're thinking, gee, does anybody really care about this? Do people use Excel in scenarios where a cluster would actually be required? The answer is, oh, absolutely. It is stunning what people use Excel for. People using Excel with clusters can find their worksheet compute time, recalculate time, cut from days to hours or minutes sometimes. It can be a real scenario. What else? I can just offload Excel logic by creating an Excel UDF, user-defined function, that runs in the cluster. Or, as I implied earlier, I can just build a SOA job where the SOA job runs its logic on the cluster. So there are various ways to use Excel in this world. They're all about the same thing. They're all about offloading Excel calculations onto the cluster to make the job go faster. To illustrate this, here's the first option of the 3. I can run Excel on each node in the cluster. I give it a workbook, probably working on different data on each node. They all do their work and send results back. Great. So the user hits a recalculate button, and the work is actually sent, probably transparently to the user, to the cluster. I haven't talked about this, just a brief digression here. It's common, not universal, but common, that the users of apps running on a Windows HPC cluster don't know it. They don't care. The app might run locally, might run on the cluster. Users ideally shouldn't care. All they know is, gee, that app runs really fast. They like that. When you think about apps running fast, when you think about HPC, high performance computing, if you are like most people, you probably think about CPU. You probably think about using lots of CPUs in parallel and speeding up an app's calculations, like an Excel scenario thinks about that. Turns out, though, that that isn't the only way to use a cluster, and it's no longer the only meaning of this acronym HPC. We are seeing the rise of this class of problems that are commonly known as big data problems. With big data problems, I can use a cluster to make my app run faster, but the goal is not to exploit lots and lots of CPU power in the cluster. Rather, the goal is to exploit lots and lots of disk drives, to let me access lots of data in parallel. Because the kinds of applications I want to run in this context are not CPU bound, they're IO bound. They're IO bound. And so to address this, Windows HPC Server has this technology called Link to HPC. You may have heard of this. It was formerly referred to as Dryad. It now has an official name, Link to HPC. And I'll tell you later why it's called that. So what are these used for? Well, the notion is that I may well want to process large amounts of unstructured data. Two key words in that sentence, large amounts and unstructured. If I have large amounts of structured data, by which I mean relational data, data in relational tables, that is not a scenario for this technology. In the Microsoft world, that's a scenario probably for SQL Server Parallel Data Warehouse, designed for this massive analysis of relational data in parallel. This guy is about working with large amounts of unstructured data. For example, suppose that you are responsible for running a big website. You have hundreds, you have thousands of servers. Those servers all create logs every day. Those logs are kind of big, and there's lots of them. And the data is just data, written out text, unstructured. You would like to look at that data because it's full of all kinds of information. User patterns, evidence of break-ins, for example. You would like to do this. But you'd like to finish the analysis before the next day begins. You can't possibly process this on a single machine. The problem is not CPU power. You are not doing anything terribly computationally intense on these machines. The problem is reading all that data. That is a big data scenario. That is a scenario for which Link to HPC is a plausible solution. And there's more. Maybe you're trying to correlate ad spend with traffic on this big site. Maybe you are dealing with search engine indexes. In fact, let me tell you something. Anybody ever heard of a technology called Hadoop? Anybody? A couple of you. Hadoop was an open source technology. It came from Yahoo. It was built by them originally and is still used by them to create their indexes for search engines at Yahoo. The problem Hadoop addresses is analogous to the one addressed by Link to HPC. Hadoop, of course, is Linux and so on. This is Windows, so an obvious distinction right there. But the problem space, the big data unstructured problem space, is analogous. Microsoft has used this technology called Dryad for a number of years. It came from Microsoft Research. So internally, for example, Dryad is used today to process Bing, do internal search analytics. Dryad was actually used, Microsoft tells us, to create the software in the Kinect controller. You know, that game controller? Because what they had was all kinds of motion capture data from people, vast amounts of it. They had to figure out the best algorithms for going from that to software in Kinect. And so they used Dryad to process all that data, the forerunner to link to HPC. Hey, did you notice downstairs over in Building C, there was a Kinect controller set up by the lunchroom? Did you see that? And people were playing games down there. I cannot get over how unself-conscious people are about, you know, doing this bizarre stuff with strangers walking by. Wasn't that mystifying? I admire their self-confidence. I really do. I would not do that, but I admire their self-confidence. So, big data. You can picture it like this. I've got this link to HPC client. I submit my job to the cluster. Logic runs on a node, accessing data on that node. Typically, that's an important point I'll come back to. Link to HPC jobs run in stages. So the first stage might work, produce some results. Those results are read by the next stage, does some more work, produces some results, read by the next stage perhaps, and so on. So the key thing about link to HPC jobs is they're about speeding up apps, yes, but not by exploiting all the CPU power. Rather, it's by exploiting access to lots of disk drives. It's about processing big data that is unstructured. All right. Let's spend some time now looking a bit more closely at the technology that underlies all of this. Let's start with management. Turns out that keeping a cluster going, creating it in the first place, is not the simplest thing in the world, because clusters can be fairly involved, especially if they span nodes with Azure and on-premises servers and desktops. Just setting them up can be non-trivial. And so here's my simple picture of the compute nodes, the head node, the client. When you look at this, all the nodes in the cluster run this HPC management service. A client workstation might well run this thing called HPC Cluster Manager, which can talk to those management services in the cluster to do various things. Things like install stuff, things like monitor the cluster. In fact, HPC Cluster Manager has 5 separate views. And those views give a good sense of what you can do with the management tool. The configuration view lets you set things up, add users, do configuration type stuff. The node management view, which I'll show you examples of in just a minute, lets you add nodes to the cluster, remove them, monitor their status, things like that. Job management, unsurprisingly, is about submitting, monitoring, keeping track of your jobs. It's not the only way to submit jobs, we'll see, by no means. Diagnostics, pretty obvious, lets you run diagnostic tests on your cluster. And finally, there's a reporting view that lets you run reports and see charts about what is happening and what has happened on your cluster. Especially with big clusters and big on-premises clusters, people have big investments. You've got 1,000 servers there. It's a big investment. To manage this well, keep it healthy, and use it as effectively as you can are all important things. Hence, this management software. Here's an example. This is the node management view. I can look at the nodes in my cluster in a list like this. In fact, down here you can see, here's how I select my views. My 5 view options here, great. Here I have chosen to see a list of nodes, lines of text, and down here is a detailed examination of one of those nodes, the one I've chosen. Great. Sometimes that is just the way you want to deal with managing a cluster. By having this list, seeing this textual information, it's just the right thing. But not always. Because in a big cluster especially, you probably want to think about things in a broader way, at least sometimes. You'd like some quick way to understand at a high level the overall status of your cluster. Can you do that by scrolling down and seeing all the OKs? Yeah, you can, but there's another option. In this very same node management view, there's this option called a heat map. In heat map, I'm seeing my cluster as squares. Each square represents a compute node in the cluster. The colors in the square represent a performance counter value. So I can set, you can see here, up to 3, or even just 1 if I want, performance counters to show up as colors in the box for each compute node. That lets me do things like see at a glance whether all of my compute nodes are having high CPU utilization. If I'm running an app, and I know that app eats up lots of CPU, and I have this view up, and I look, and my colors all show low CPU, I know at a glance something is wrong. The point is, this kind of view is meant to help the administrator of the cluster intelligently, quickly, easily understand the cluster's health, the cluster's state, and know something about jobs running on that cluster. Speaking of jobs, what happens when you actually run a job? Well, let me show you. There's a client. There's the head node, which, as we saw earlier, has scheduling software. It's called the HPC Job Scheduler. You submit a job to the scheduler. I'll show you in a moment there's lots of ways to do this. The scheduler then queues the job. It queues the job because it's very common today that clusters have lots of users. If you have your own personal cluster, that's a glorious thing. In most organizations, you don't. You've got a cluster that's shared across lots of users. It's an expensive resource. One might imagine, as clusters built on Azure become more common, the need for queues might at least change. But certainly with clusters built from on-premises servers, the queues are important. The job is queued, and at some point the scheduler decides, okay, this is it, let's run this job, and the job's logic gets spread across compute nodes in the cluster, each of which has a node manager that the job scheduler can talk to make this happen. The user who submits the job can also monitor it with this thing called the Job Manager Console. It turns out the Job Manager Console is actually the software behind the job management view in the tool I just talked about, HPC Cluster Manager. So they have the exact same user interface, which I'll show you in just a moment. But first, as I've said several times, it is possible to submit jobs in a variety of ways. A command interface. There are PowerShell commandlets for doing it. There's a .NET API. If you want to build an app, a .NET app that submits jobs to the cluster, go wild. There's a browser interface to submit jobs through a browser. There's a bunch of options here. Once your job is submitted, it's in the queue. And the HPC scheduler will then choose your job to run based on various things. There are two big scheduling options it supports. Number one is called queued. It's what it sounds like. It's FIFO. It runs jobs in first in, first out order, except jobs have priorities. And so higher priority jobs can jump to the head of the queue, as they should. Option number two, balanced. Balanced is interesting. Balanced looks at the jobs in the queue and takes as many as it can, gives them the minimum resources they need, and starts them. I didn't tell you this. When you submit a job, you tell the scheduler what you need for resources. So it can look at them and it can say, you know, in the queue, I've got these 5 jobs, and they've asked for this as a minimum. Do you know what? I can run all 5 of those. It starts all of them, and then it gives resources that are left to higher priority jobs. Not strict FIFO, but a more balanced way. If you care about this stuff, it turns out there's lots more complexity in the scheduling algorithm. There's a bunch of stuff you can do because they've gone to a lot of trouble to help people exploit and make good use of what could be this very expensive resource of a big cluster of servers. Thinking out loud, one wonders if that will matter as much in a world of Azure-based clusters, where you're paying by the hour for your nodes and shutting them down. We'll see. We'll see. Here's an example of monitoring a job. And again, you might see this through the job monitoring tool or through HPC Cluster Manager. Same view. There is a list of jobs currently running in the cluster. You can see various things about them, their state, their progress, who owns them. And as before, you can examine those jobs independently down here to learn more about them. And notice this, in the upper right, there's a job submission option. Yet another way to submit jobs. There are lots of ways to submit jobs to the cluster. There's a few more things worth talking about in this. One of them is what actually happens when you run a SOA job. Because it's kind of interesting. There's a little bit of, I wouldn't say complexity, but some diversity here. Here's what happens. You've got a client. You've got your head node running the scheduler, as always. The client submits the job. The scheduler queues it, and at some point, it starts. SOA jobs are built as WCF services. Great. Now, the client can invoke operations in those services. Wonderful. But the client doesn't do that directly. Here's what actually happens. What actually happens is, once this occurs, there is a broker node. The HPC job scheduler hands off the job to the broker node. It then tells the client how to find the broker node, and the client then passes its requests to the broker node, where they get sent on to the actual services in the application. Results are sent back. Why do they do that? Scalability, primarily. If all clients send all their requests to all running SOA job services through a single head node, that would not help the goal of this whole technology, which is speed. So broker nodes let you pass that work out onto separate computers and thus speed the whole thing up. It's also worth spending a bit more time, I think, on link to HPC. There's no way to know, but it's plausible that this aspect of Windows HPC Server will become a substantial part of its customer base within a few years. Let me just ask, who in the room thinks, from what I've said so far, that they might have in their organization problems that are big data problems in the sense I've described here? Need to process large amounts of unstructured data in a reasonably quick time. More than half of you. Right, I'm not surprised. Again, I hate to belabor the point, but I think we're very likely at the beginning of a renaissance of cluster computing, where new kinds of nodes and new kinds of apps make this a much more mainstream, much more interesting technology for a wider swath of people than has been true up to now. So what's happening here? What's happening is this. As I said, this is the latest option, the newest thing added to Windows HPC Server. There are some challenges. One of them is storing big data. Because you remember, we're trying to store this data in the cluster somewhere. Well, where can I put it? Well, the cluster nodes all run Windows. Let's put it in a Windows file. Sure. Except big data, by definition, is big. And so it won't fit a single file. So what do? Well, I could just put it in lots of files and make the poor person building the application just deal with all these different files. I could do that. And no one would use the technology because it'd be too hard to use. Developers want a name. They want a name for their input file. That is the problem that's solved by this thing called the DSC, Distributed Storage Catalog. I will show you how in just a minute. It provides a way to store large amounts of data in the Windows file system and give them a single name so developers can work with them in a direct way. The next problem is working out how to write applications. Because to go write the code for an app that processes big data on a cluster can be non-trivial. The approach taken here is evident from the name. The technology is called Link to HPC because the way you write big data apps on Windows HPC Server is by creating a LINQ query. If you don't know what LINQ is, it's an acronym for Language Integrated Query. It's an addition to .NET languages, C#, VB.NET, that lets you essentially embed queries right in the language. So I don't actually put a SQL query in the language, but rather the language itself gets keywords like select and so on. So I can have queries right in the language. In this technology, the way you build an application to process this big data is by writing a LINQ query. It's actually fairly straightforward. What happens is, as we'll see, when the query executes, the Link to HPC technology generates the job you need. So let's discuss these two things. First, the DSC. Oh, notice one thing. Notice that throughout this section on Link to HPC, I'm always showing the cluster as containing only on-premises servers. That's because in this very first release, it only runs on on-premises servers. Microsoft tells us that will change relatively soon, adding certainly support for the cloud. But right now, this is the one of the 4 categories that runs only on premises today. So here we go. To use DSC, what you do is take your data, your big data, and you put it on the machines in the cluster, broken up into these things called DSC files. DSC files have no defined size, up to you to choose. And a DSC file is actually just an ordinary Windows file. That's it. It's a Windows file. Except it's a Windows file whose location is kept track of by the DSC. Distributed Storage Catalog. The DSC knows that a group of DSC files together comprise this thing called a DSC file set. And so when a job starts running on the cluster, the job contains the name of its input DSC file set. It's possible to find all of the DSC files in that file set by just checking in the catalog. It knows where they are. An important point here. DSC files, once they're created, can't be changed. A DSC file set can be appended to, but you can't change things. It's meant to be read. Think of this as being akin to a business intelligence technology, a BI technology. It's about reading data. It's almost like data warehouses in a somewhat constrained way. They're read-only. Do not confuse this with some kind of interactive transactional SQL Server database. This is about processing, reading large amounts of data. In fact, frequently, today, in these kinds of big data apps, people only read the data once. Think about my earlier example of all the log files from web servers every day. You read those guys once, throw it away. So these are really for big read-only scenarios. This is not some update dynamic database for giant data. Not at all. Not at all. It's for processing, which means reading big data. Hence, the DSC files, once they're created, are immutable. They're read-only. To understand why this thing even works, how it helps, how it runs apps faster, you've got to understand this notion of data locality. As I just showed you, a DSC file set, the thing we're processing, is in fact built from some number of DSC files, I show here as data, on each machine in the cluster. When you run a Link to HPC client, the LINQ query is executed, and the result is an actual Link to HPC job. There's this software that works like a query planner, really. It generates the job from your query. Then, this is important, the logic in the job is assigned to run on the same machines as the data that logic works on. So here I have 3 machines in my cluster, each of which holds one DSC file, one piece of the data in this big data set. When HPC server assigns the job, it figures out where those guys are, and it starts the job's logic on the same machine. Data locality. The logic is now reading from a local disk, much faster. Now, it turns out, as you go through all the stages of the job, you can't always do this. But at least for the first stage, it will do as much as it can. It will assign logic on the same machine as the data it's working on. That data locality is fundamental in making these kinds of jobs run fast. So just to paint the whole story here, here's what happens when you actually run a job. You've got your DSC file, which you created via a command line or an app you wrote or something. You must create this before you do this. That's your input, your processing. Maybe that is, for example, a whole bunch of web server log files. If you are a search engine, maybe that's a whole bunch of links from the web. If you are the kinetics people, maybe that's a whole bunch of motion capture data. Whatever it is, it's lots of unstructured data in Windows files, which are called DSC files here. Then, you've got your client, which executes the link query. That thing winds up spitting out the job that goes to the job scheduler. It gets queued, like always, and the job runs. Great. But when the job starts, it doesn't yet know what nodes to start the job's logic on. Because recall, data locality means that the job's logic needs to run on the same machines as the files in the DSC file set. So the job, this piece called the graph manager, actually goes back to the DSC and says, where are my DSC files? Where are the DSC files in my input DSC file set? When it finds those machines, it's then able to start the logic for the first stage of the job, and it processes. So that's how this thing called Link to HPC is able to run big data jobs in a way that's fast enough to provide real value. Let me wrap this up. Here's a simple two-dimensional graph that I find to be a useful way to think about what is happening in cluster computing. Notice, the horizontal axis is kinds of compute nodes. The vertical axis is kinds of applications. So using Windows HPC Server as a measure of what's been happening here, in the beginning, like 2006, there was one kind of app, MPI jobs, that ran on one kind of compute node, on-premises servers. A couple years later, now we had MPI jobs, we had SOA jobs. Okay, good, that's progress. Still on-premises servers. A couple years after that, MPI jobs, SOA jobs, Excel, on-prem servers, and desktop workstations. And now, MPI jobs, SOA jobs, Excel jobs, big data jobs, on-premises servers, workstations, Azure nodes. This is significant. This is a change, I think, that's worth noting. Because what we're seeing is a progression from simple and focused, and let's say relatively narrow, to broader and more general purpose, broader applicability, easier access to the power of cluster computing. I'm not kidding. I really believe it is entirely possible that we stand today at the dawn of the renaissance of cluster computing. Thank you.